We'll start, and I hope you all had a relaxed weekend. I certainly did. I went to a cooler place, cooler than here. Before I think I was talking to Zhao Junbai, the host. He was saying the format of this week maybe slightly changed compared to the previous 2 weeks. Oh, here. Zhao Jun, I was just mentioning you were talking about the change of format, or do you want to talk, or maybe we can? The lecture format is still the same. It's still the same. Yeah. So it's mainly in the afternoon. Yeah. So then we'll coordinate with Renkang later today. When he comes, then we'll. Right. So there'll be more, more interaction. Hopefully, let's work. Okay, so. We'll start to recap what we left from last time. We started a little bit introduction about parallel sparse factorization. After we have seen all the combinatorial issues, the ordering symbolic factorization algorithm, now we're ready to do the numerical factorization. By the way, I mentioned basically the 4 big steps for sparse direct method, like ordering, symbolic factorization, numerical factorization, triangular solve. And among all of these, if you look at a sequential profile, this numerical factorization takes up, in most cases, probably takes about more than 80% of the total time. So the ordering, it looks like very complicated, but it's all combinatorial integer operation. And it turns out when you do properly, you can get very fast algorithm. So that's why over the years, people have focused more on parallelizing numerical phases, factorization in particular, and then numerical triangular solution. So we'll talk about 2 different classes of machines, then the algorithm would be different. So this is the shared memory algorithm. And also, remember, we talk about a very different organization of the data flow. You could have a left-looking algorithm, right-looking algorithm, and a multifrontal algorithm. Depending on the different data flow organization, then you can design the parallel algorithm will be also very different. And throughout this lecture about parallel factorization, I'll focus on one kind of data flow organization. For the shared memory, is left-looking. For the distributed memory, is right-looking. And in particular, those are very well implemented in the software we have developed in SuperLU library. But then I'll give you pointers to a lot of other packages. They might use a different parallelization scheme. So in the shared memory algorithm, it's relatively simple. So your matrix A and also the LU factors, they all sit in the same big memory, which you can access. And at any point, for this is a left-looking algorithm. So what we do is sequentially, every time I just marching through this panel, several columns from left to right. Everything to the left, if you are at the current panel here, everything to the left, LU, are already finished. And everything to the right is not yet touched yet. So your matrix A here is not, you haven't touched that part of the matrix yet. For the shared memory algorithm, what you can do, relatively simple, is you follow this elimination tree, which gives you a good order of task dependency. And then in the global organization is we can set up a global task queue, which is the queue of available tasks. Each task is one panel factorization. So in the beginning, for example, the bottom of the leaves of the tree, they are freely available to be factorized. So they don't have any descendant depend on them. So they are free. So you can, in the beginning of this algorithm, you put all the leaves of the panels put in the task queue. And every process in this case is we have a shared memory. So you can think about in OpenMP term, every thread will come to this task queue to pick up a free task, which means pick up one panel to do the factorization. And then, as I mentioned the last time, that so this is one thread is doing the factorization of this panel, another thread doing the factorization of this panel. And look at this dependency graph. So P1 will need to accumulate a lot of updates from the descendants. And P2 will accumulate a lot of updates from the descendants here and also some of the descendants here. But P2 will also need to update to the two columns here, for example, from P1. So then P2 doesn't need to wait for, those are already finished. So P2 only needs to wait for P1 to finish those guys. And once P1 finishes those guys, it will send a signal. And this is through synchronization mechanism we have used maybe some counter. We'll send a signal to P2, say, I'm done with those. So you can use these columns to update your columns. So those are that you can imagine you can have 16 of those threads. They are taking care of the different part of and they have to make sure that they wait for all the other threads to finish all the dependent columns in the end. So let's see, once this P1 finished its subtree, then it's for example, like here, when both of these guys, they finish the subtree, then they can decrement the counter of the parents. Once the parent counter, dependency counter becomes 0, then that means that this panel becomes free. Then it's put in the task queue. Remember, we have a task queue. Then the other thread could come to the task queue to pick up a task. Okay, so the threads interacting with the task queue when taking the task from task queue is concurrent read. You don't need the lock. But when one of the tasks becomes free, when it's put back in the task queue, then you need a lock. Make sure that only one process, one thread, is modifying the task at the same time. So that's how the algorithm organized like this. So we can take a look at the performance of this algorithm on the current machine. And as I mentioned, this code was developed about 10 years ago, a little more than 10 years ago. At that time, we benchmarked only on the machines at that time. And now we say, look at the same code. Can we get some good performance without changing the code? So that would be good. So we look at several matrices here. One is the economic model, which is very different from the PDE problem, say finite difference, finite element. But these two, they are from, in the biological application, they look at the structure of the stomach, the torso, the body, and do some simulation. So both are three-dimensional using finite difference scheme. And that one is a circuit simulation. It's a nonlinear analog circuit. So the dimension of the problems varies. So the small one is about 60,000. The larger one is here is about 259,000. And then this is the number of non-zeros in the original A. And we look at the field, the number for the field. So these two columns is just to compare. We have two different codes. One is this MT is multi-threaded code for shared memory. Another one is, I'll talk about soon, is the distributed memory code. We just look at the field. They look roughly the same. And then the average supernode size. Remember last time we talked about supernode, we group several columns. If they have the same structure, then we group them as a supernode. So you see that for sparse matrix, average supernode size is actually very small. The largest is this matrix 4. Stomach, the size is only 4 columns. That's only the average. And in fact, if you look at the supernode size, if you do a profile, then you can see that throughout the factorization in the beginning, they are very small. A lot of them supernode just one column. They don't have any similarity in the beginning. But throughout the factorization, as you proceed towards more the end, then you get a big supernode. For example, you think about nested dissection. right? Remember we're talking about the separator corresponding, the submatrix corresponding to the separator part is always dense. Those are actually supernodes. And then, of course, towards the end, the separator are bigger. So when the top level is biggest, then you cut by half. And the previous level, those are earlier levels, become smaller, smaller, smaller. So even from a nested dissection point of view, you can imagine intuitively the supernodes are getting larger towards the end. So the average actually doesn't say too much. It's really you have to look at the profile of throughout the factorization. Okay, so these are two multi-core systems. It's about 4 or 5, maybe 3 or 4 years old. I didn't have time to to do the new benchmark before coming here for the latest machine. So one is the from Intel Cloverton. It's a Xeon processor, 2.33 gigahertz, and the peak performance of each core is 9.3 gigaflops. So they have 2 sockets, then 4 cores per socket. And the second machine is from Sun Microsystem, is called Niagara 2. And it's a Spark architecture. It's a T2 generation. The peak performance is, each core is relatively simple. It's less, it's lighter than this one. So each core performance is only 1.4 gigaflops. But then it has a large amount of parallelism. If you cannot exploit, you really don't get good performance. So here you have 2 sockets, 8 cores per socket. And then there's something called hardware threads per core. So this thread is hardware. At the hardware level, it's not a UDO, OpenMP, open spawn threads, etc. So what does that mean is they have a very lightweight, each hardware thread you can think about as a very lightweight small CPU processor. And then it carries registers. It can do some floating point operations. So it's a complete, like a complete processor, but it's very lightweight, consume much less power. And when you have, you can arrange your program nicely, then the compiler could generate an instruction sequence so they can split the different part of the work to different threads very nicely. And also hardware can do the task, the thread migration. So that means if this hardware thread is over-committed, then they can automatically, runtime system can move some of the task to the other more freely available thread. So that's all happening underneath without a programmer intervention. So that's a very nice feature. But then you can imagine that this machine, you could have for like 8 by 8 by 2, so which is 128-fold parallelism potentially. And here you have like 8-fold parallelism. But let's see what the code does on this machine. So on the left is Intel Cloverton. That one I said you could at most get maybe 8-fold speed up. And then it depends on matrices. We have 4 here that you can see. So here I'm plotting the speed up. So you can see that with increasing number of threads, the code always speed up a little. But depends on matrices. Some matrix you could get a very good speed up, and some you get a slightly less. And some of them, like this matrix, this is from economic modeling. It doesn't have a very good, nice structure, and in fact the parallelism is quite limited. At least this kind of algorithm. So it varies depending on matrices. And then look at this Niagara 2, the Sun. As I mentioned, potentially, in theory, you could get 128 speed up, right, fold. But then you increase the number of threads. So actually, it's saturated by the time you increase to 64 processors. So you can, most of the matrices, you get a speed up to 64, and then it drops. This is mainly because at least for this kind of matrices or this particular algorithm, you actually have saturated the hardware resources. All these 8 threads per core and 8 cores, they share the common bus. So once you saturate the bus, even if you increase the number of threads, you cannot really utilize, get speed up anymore. But still, it's, for this kind of machine, it's very cheap. And you can get like it's not a 64, it's like 20 speed up, but you can increase reduce the runtime, keep it reducing up to 64. So that's quite effective. Okay, so let's talk about the distributive parallel factorization. And I mentioned in the first or the second lecture when we talk about dense factorization, how do you, or dense factorization or dense, say, LU Cholesky QR, a lot of these algorithms. The first question you want to ask is how you got a big matrix, say a million by a million. How do you want to distribute the matrix, right? Cut the matrix into pieces and send one piece on one processor, one piece on another. So the standard way to do that, one is 1D blocked. So you give processor 0, 1 panel, 1, 2, like this. The whole matrix is split by this. Or you can do row-wise. And then a slightly better way, because in this way, when you do LU factorization, by the time you get to this point, then all the other processors, they are idle. They don't have work to do. So then a better way, they say, OK, we'll do cyclic. So we cycle through all the columns like 0, 1, 2, 3, 0, 1, 2, 3, so that by the time you get to here, then you still have every processor is involved in the calculation. So this is slightly better. And then for the cyclic, you can imagine that you have all the little pieces. You can get a very big GMM, the +3 operation going. And then people say, oh, OK, we can do block cyclic. It's somewhere in between these two. We partition into blocks of certain size, say 100. And then we cycle through these blocks of all the processors. But it turns out that with this scheme, when you do LU or QR type of factorization, you still have a lot of communication among the processors along this direction. So what people in the end have settled with more sophisticated, instead of doing one-dimensional this cyclic, then you can do two-dimensional block cyclic. So you still do partition the block in this way, partition the block in that way, and your process is also organized as a two-dimensional mesh. So in this case, I have 0, 1, 2, 3, 4 processes. So your matrix is partitioned into blocks, and then your processor basically think about it as a stamp, a template, just a stamp replicate on all these different blocks. The nice thing about this is really a compromise a lot of things. So you can have better load balance, because at any point of factorization, you always have all the processors are actively working, and they have roughly the same amount of work. So its load balance is good. And the communication-wise, when you do this side communication and that side communication, you only involve square root of p processors, right? Since you have a two-dimensional processor grid, if it's a square grid, then you only have a square root of p processor doing this way communication, square root of p. So the communication is reduced. It's relatively better. And then you have blocks, and you can do the bigger GMM. So that's the advantage. And there's if you go back to the scalar packet design, for example, there are a lot of papers about almost 20 years ago, starting analyze the LU-QR Cholesky and analyze the communication pattern, amount of communication of this distribution versus that or versus those. So it turns out asymptotically, this one has the smallest amount of communication. Okay. Okay, so we can borrow the similar idea from dense calculation carried to the sparse calculation, and it's very similar. So I have here I have a sparse matrix, right? And the difference is some of the blocks may be 0, entirely 0. because of the sparsity. So, and also all these blocks, the size, they are not of the same size because of the different supernode size. So essentially my partition of the blocks, I need to follow the supernode partition. And then I do two-dimensional since it has better communication characteristic. So I do one-dimensional partition based on the supernode size, and I apply the same partition to the row-wise as well. So then some of the block, for example, like if you look at this supernode, it will have a non-zero diagonal block. It's fully dense, and then some of the non-zero blocks here, some of non-zero blocks, and the rest of the block, those are zero. So those zero blocks, I don't need to store, okay? And then how do I store this part of the matrix is, so imagine that at this active panel here, in this figure I have 6 processors, 0, 1, 2, 3, 4, 5. And then for this block column, I have for 2 processes, 1, 4, 1, 4. They are the owners of this block column, okay? And then look at 4. So 4 only has this block, that block, and this block. 4 has 3 blocks. So actually these 3 blocks in process 4 memory, they are stored contiguously in the memory. That's the non-zero value. But then you have to, you can imagine that because from the matrix, global matrix mathematical point of view, the indices are across the global, they are not contiguously in any way. Then you need a separate set of indices to store those block indices. So that's the basic storage. You can use your favorite compressed column storage blockwise or compressed row storage, which we studied in the beginning. So that's the storage. And then for 1 here, for process 1 here, it actually doesn't have, it's a 0, it doesn't have anything. Okay, so because of the sparsity, at some point, at some step, at this step, some processes, they don't need to do any work. And that's the difficulty for the sparse factorization is it's hard to get a very distribution which makes sure everybody is busy all the time. It's always you have these bubbles. Some of them, they don't have data, they don't need to do work. And some of them, sometimes maybe they have less data, they do less work. So that's in the sparse case. The load imbalance is a serious problem. So once you get this distribution, similarly for the row, for the U part, then you do the LU factorization. It's a parallel. This to get the L part is a parallel among 1, 4 processes, and then along the row-wise is a parallel U among the 3, 4, 5, 3 processes. Okay. And this process grid is flexible. It doesn't have to be power of 2, or it can be any. So for example, if you have 5 processes, you can say 1 by 5 or 5 by 1. It doesn't need to be power of 2 or anything. So it's a general scheme. Okay, so with this factorization, then the steps that we need to take for this particular algorithm is we have to worry about stability and the parallelization, factorization, and the solution, etc. So we still follow the several steps. The first pre-processing step is we do static pivoting. So we use we permute A unsymmetrically to put large elements on the diagonal. And I mentioned that briefly in a couple of days ago. So the algorithm we use is weighted bipartite matching. So you can take a closer look at this algorithm. So this is your original matrix. Start with A, and in fact here I have several entries on the diagonal. They are 0. So if you just do this factorization without pivoting, then you hit 0 pivot quickly. Okay, so it's not good. And then the graph model here we use is the bipartite graph. So we divide into row set of vertices and a column set of vertices. For each non-zero, I put an edge. So 1, 1 has an edge, but 2, 2 doesn't have an edge. 2, 2 because 2, 2 is 0. So you put this, set up this bipartite graph. And my question is, can we find a permutation of row permutation so that I put a large element, among those entries, 5 of them are the largest, let's say. So I want to put these 5 largest to the diagonal, just relabeling the rows, permute the equations. The way to do that is to represent A as a weighted, undirected bipartite graph. Then you find the matching. The matching is a set of independent edges so that they have the maximum product of weights for this algorithm. So then you look at each edge corresponding to non-zero. So you find the edges, the 5 edges, which has the largest entry in terms of the product of those 5. Then those edges actually give you a good diagonal, the diagonal relatively big. So in order to put that onto the diagonal, so you essentially just need to permute these row vertices. Instead of 1, 2, 3, 4, 5, you do 4, 5, 3, 1, 2. Then those light blue guys will be on the diagonal. Okay? So you get a good diagonal. Then you permute rows to place matching on diagonal. You put matching on diagonal. So once you do the permutation, then the picture of a bipartite graph will be each of these horizontal diagonal edge will be corresponding to one of these light blue edge. That's your diagonal. And it also gives, this algorithm can also give you equilibration row and column scaling so that the elements below the diagonal, they are bounded by 1. So then you got a good, after this pre-process, you get a good pivot sequence. So then the second step is scale rows and columns to equilibrate. So then the fourth step is to do the, during the factorization, then we don't need to do pivoting anymore since we assume that we already got good pivot sequence. And when you, throughout the factorization, suppose you still encounter some very tiny element on the diagonal, then you don't want to divide this. You can say, I replace this diagonal by a little perturbation. In this particular case, is a half precision perturbation of the diagonal, so that you get a factorization. It's still accurate in the backward error sense. It's you lose half of the precision. So that's the a little bit trade-off of stability and parallelism. Okay. So let's go through this parallelization a little bit closer to see how it works, the numerical factorization. And to write down the algorithm is actually quite tedious, but we'll just look at big steps. So the first, to summarize, the first is matrix pre-processing, and then you do the symbolic factorization, which compute the elimination tree, the structure of the LU, the communication on column scheduling, and you find the supernodes, then partition the supernodes into these blocks. Then we do the numerical factorization. Time-wise, this is dominating. So the pseudo code of this is essentially, I went through the algorithm already. You go through the algorithm. The outer loop is from 1 to number of supernodes, right? So it's a panel factorization. At each step is this is your jth step. You do the factorization of the jth to get the jth L, and then you do the factorization to get the jth panel of U. Once you get that, you use send. This is actually corresponding to a MPI send to the processor columns. And also, so you need to send this U part to all the processes here, and then send this L part to all the processes to the end. So these two pieces, because they are sitting on different processors, so once you send to all of the other processes, when they receive them, they can do update to the destination columns. That's your short complement update, right? So the other processes, they have to wait for LJJ. So here is the LJJ, the diagonal, and then factor this row, and then send this right to here. And then wait for UJJ, this part, to factor this column here, and then send it down to to process. This is a send write to process row here. Then you do the trailing matrix update. So the trailing matrix update here is once everybody received the column of L, row of U, trailing matrix update is entirely parallel. So they don't, because they have destination is they have different pieces of the matrix, they don't need to wait for each other. So this part is parallel. Those part needs some synchronization to send the data to the others. Then you can imagine for these algorithms to scale up, the bottleneck is really the panel factorization. At each step, the first step you have to finish this, finish that, and send for the rest to do the update. And the second step, you need to finish this, finish that, and the rest has to update. So then if you draw the timeline of this algorithm, so you always have sequential panel 1, panel 2, like this going through. So the panel factorization has sequential flow. There's a very limited parallelism. And then all the processes, they have to wait for diagonal factorization and the panel factorization. So it's actually not very scalable. If you just code it up like this, it looks simple. Then we look at the performance of this earlier version of the code. It's the CPU distributed 2.5 version, 2.5 and previous. For quite some years, this code has been has used this algorithm for a long time. So here I give you the two matrices. One is the accelerator modeling problem I mentioned in the big application. When they do the accelerator structure, then they need to find the best shape and need to solve the nonlinear eigenvalue problem. But in order to get the interior eigenvalue, you have to solve a very difficult indefinite linear system. And very often, factorization scheme works best in this case. So that's why these application people, they still use a direct solver in their production code. So this is one of the problems. The size of this is 2.7 million. That's the dimension of the matrix. I think for this matrix, roughly on each row on average is about no more than 100. So it's probably 70, 80 non-zeros per row. But the dimension is 2.7 million. It's very big. And the field ratio is not too big. It's 12. So it's the number of non-zero in LU versus in A. And the picture, the plot I'm showing you here is the increasing the number of cores on the Cray, this Cray machine, up to 2,000 cores. And then the factorization time, vertical axis. So that's the total factorization time. And then among the total factorization time, I did the profile of the communication cost. So this red time is actually the amount of time spent in the MPI communication. And then you can see that the code, you can only up to 128, you get a total time reduced. But then beyond that, most of the time is actually in the MPI communication. It's not in computation, right? And then even if you put in more processes, the time actually goes up. So that's one case. And another case is DNA. It's from genome application. So in this case, the matrix is relatively small. It's only the dimension is 500,000. So its dimension looks smaller than this. But on the other hand, the field ratio is huge. So for sparse factorization, one of the criteria to look at is really the field ratio. The field ratio is big, meaning you have to spend a lot of time to do the calculation. Also, you have to store the matrix, right? Because you have to store the LU factor. So these two matrices, even if it looks like this is a smaller matrix, but in fact it's not. After the field ratio like this, you have to do more work. And if you look at the time factorization, this one on 32 processor, it takes 2,000. But that one on 32 processor, it takes only 15 seconds. This is 2,000 seconds. So for sparse matrix, it's very complicated. You cannot, people give you two matrices, of two different sizes. Then you will say, oh, this is faster than. It's actually, you have to look at, in the end, what's the ordering algorithm you can apply to get the best ordering, and what's the field ratio. And you get, if you are unlucky, you cannot get a very good ordering to get a very reduced, the LU factor size, then you have to pay a lot of cost. But then the point of here is that by the time you get to 2,000 processes, the cores, the total time still reducing a little bit, so it's good news. But then most of the time, in fact, for this case, 96% of the time is in the MPI communication. So it's all about communication. It's nothing about operation. So then we get rethink about this algorithm, see whether we can do a little bit better instead of sequentially waiting for each panel to finish. So the code is, the pseudo code is even complicated. But the idea is relatively simple to explain. So you see the difficulty with the previous algorithm is when you do this panel factorization, the other processes, they are waiting there. They're not doing much work. So what we're trying to do here is to set up a window, which we can say look ahead, to try to finish the sequential path as fast as possible. So what does this do is at the jth step, we have a look ahead window of size, for example, 10. Usually in the code we set to 10, which is good enough. And then we say after we factor this, at this step j, after we factorize this column, then we'll immediately send to the next column processes. And then the next column process will immediately, instead of waiting for the whole short complement to finish the update, but it will immediately to start the factorization of this panel and send it right away. So these window, like 10 of those panels, they actually set up as a pipeline. Remember the beginning we were talking about pipeline? So they are, in the early algorithm, they are separate stages. Now I'm dividing those stages, I try to pipeline together, so steal the time together. For example, when these processes, they are finish the factorization, when 1.4, they are doing the trading matrix update. Then these processes, they are actually doing the computation of the next column update. So you have the overlap of communication of the previous step with the computation of the later steps, or the communication of the current step, the computation of the current step with the communication from the previous steps. So once you set up this pipeline, you shorten the entire sequential critical path, we call that. So that's the pseudo code you can read later. So then to get this to work, in the dense case, it's relatively simple because in the dense case, your dependency graph is one after another. But in the sparse case, remember, if you look at the elimination tree, you can have some different subtree, they can be irregular. The dependency is a little bit irregular. That's why in the beginning, I talked about all these different graph models. And those are very helpful when you design the parallel algorithms. So we can use a different different graph model to help to organize this dependency. So one thing you can take a look at the whole graph, entire graph. But usually we don't use this because this LU DAG is big. It takes a lot of memory to store. So then we can talk about the transitive reduction of the LU DAG, which gives you the minimum dependency, but still remove a lot of edges. And there's something called more technical symmetrically prune the LU graph, which we use. So in our code, we actually use these two graphs. Another one is the elimination tree, which is relatively simple. But in the non-symmetric case, we don't have good way of doing that. So we use elimination tree of a symmetrized matrix. So the thing is here, there's another issue of reordering coming into play. Is let's say suppose I set up my window size to be 5, and I use this particular tree structure which is ordered by post order. That means the post order just means all the subtree numbering are smaller than the root of this subtree, and then the subtrees, they are ordered sequentially, like 1, 2, 3, 4, 5, 6, 7, then 8, 9, 10, like this. So if you do this, use this post ordering like this, suppose your window size is 5. And in fact, the first 5 columns, you don't have any parallelism, even if you say I set up the pipeline of 5. But they have to go sequentially most of the case. Only this 3 and 2, 3 and this branch, they can go a little bit parallel. So you still don't have enough parallelism exposed. So on the other hand, if I renumber this tree, relabeling, also reordering, using the bottom-up level-based ordering. So that means I have all the leaves is labeled first, 1, 2, 3, 4, 5. And then the second level is the parent of the leaf, which is 6, 7, 8. And in this case, at least the first window, 1, 2, 3, 4, 5, they are all independent. So your pipeline actually works better in this case. You don't need to wait for anybody, at least the first step. But of course, later you still more and more dependency comes into picture. So what we found is just setting up this window, this pipeline, we actually get a speed up only like 10-15%. It's not very significant. But then after we apply this reordering, trying to expose more parallelism within the window, then we get a significant speed up. So the same, I think it's the same matrices here. So that's the accelerator, and then what I'm comparing here is the 2 versions. One is the old version, one is the newer one. This one was about 2 years, less than 2 years old. It's on the web. When nowadays you download the latest version, it's this one. So then you can see that I still plot so these 2 bars, one is old version, one is new version. I still plot the total time with increasing number of cores, and also the red stuff is the MPI. So you can see that by the time you get to 2,000 cores, the speed up could be more than 2 times compared to the old version. And then the portion of the MPI time is reduced, although it is still quite dominant in this case. And for that case, it's even more significant. So by the time you get to 2,000, your total time is reduced a lot, and then the MPI actually in this case is reduced a lot. And also this is matrix dependent, right? It depends on how much reordering, this reordering is effective to expose parallelism within the pipeline window. So the future work which we are working on is to look at some more sophisticated scheduling scheme and also hybrid programming, which in one of the projects I mentioned is to do the hybrid GEMM, the MPI GEMM code, adding your threaded GEMM on each node. So that's something we're looking at because nowadays we have a machine, each node is very fat, has 20 or 30 cores. And if you do purely MPI on each node, in fact, you get a lot of synchronization overhead there. So that's some of the future work. So let me, before we close the parallel algorithm, then we'll take a look at the performance of this distributed memory code on different matrices. And here I get a matrix of a relatively bigger dimension. For example, for one of these matrices from quantum mechanics, chemistry calculation, it's a complex matrix of over 4 million degree of freedom. And this is the sparsity measure on average number of non-zeros per row, and also varies. For this circuit simulation, they use the M&A method from IBM. It's a complex matrix, but to begin with, on average, each row has over 4,000 non-zeros. So in our standard, this is actually relatively a dense matrix. And then the field ratio varies. So this one has a 56, it's get a lot of field. But the circuit matrix, it has a very nice pattern. Even if you start off very dense, but it remains like that. It doesn't feel at all, right? And then the performance on, this is a few years ago, older machine. So again, if you look at the factorization time, the speed up, here is the time. depending on matrices, for this G500, it has a lot of field. You get a very nice supernode structure. So you got almost a linear speed up, even from 32 to 256. And this one is so big, it doesn't fit for a smaller machine. So the memory requirement is huge. You have to use at least a 32 node to store this matrix. And then for this guy, this is one of another example. It's a different accelerator structure. So it gets reduced here, but then it doesn't go beyond that. And that's the triangular solution time. So you see the curve of a parallel triangular solution. It's much flatter, meaning that it's actually scale worse than the factorization. So the situation here is a triangular solution. It doesn't take too many operations. Just to look at the time, absolute time, it's actually very small. For example, here is only like for this matrix, for that matrix, let's see, on 32 processes, the triangular solution is only a little over 20 seconds. But on 32 here, it's 100, 200, 300. So it's hundreds. So usually triangular solution, it takes less than, say, 10% of the factorization time. But because of lower arithmetic intensity, it doesn't scale very nicely compared to factorization. So if you do the detailed performance analysis of a triangular solution, you will see that even more time is spent in communication. There's not much operation. So it's, if you look at arithmetic intensity, remember we took a look at that in the beginning. For triangular solution, it's roughly 1-to-1. So it's all about communication. So then for this biggest machine, biggest problem, you can see the runtime. This is the quantum mechanics problem. Complex runtime is reduced very nicely up to 1,000. And the triangular solution is not very scalable, but it doesn't take too much time. Okay, so let's take a look before we take a break. We look at the distributed triangular solution. So why is it communication intensive? It's not so much operation. So this picture shows I have finished factorization. So your LU is already sitting on the processes like this. So by the way, if you design a parallel factorization algorithm, your triangular solution has to be parallel. Because your LU is distributed, you cannot collect that into one node, then do sequential triangular. So once you are done with the previous stage parallel, all the rest of the stage has to be parallel, even if it's very difficult to do. So the ith component is, we take the inner product version. So the ith component of this guy, look at this guy, is the Lij times xj, all the previous row times all the components you have computed and subtract from bi, then do the divide by this Lii. And then because of distribution, so the first, so I have non-zeros here and here, right? So the first step, I need to get the x, the second component of x get sent to here. So that's my first step. The second step is this component of x needs to be sent to here, processor 1. But in this particular case, it happens to be all on one processor. So this communication is just a read operation. It's a local memory access. And once you get that, the third step is you have to do this addition. So addition is this, right? And then the addition is done. It has to be sent to the diagonal process. In this case, it's 0. So this, after this addition, local accumulated addition is sent to processor 0. And then subtract from bi to do the division. So you have communication here, and could be potentially communication here. Then this addition is local, and then communication here. So it's a lot of communication. So that's the general situation of this parallel triangular solution. And here I gave you some performance of two different machines. One is on the shared memory machine, the Cloverton, which we saw before, 8 cores. And then I have increasing the number of tasks. So you can see that this is actually the time. And what I'm comparing with is we have improved the code. The old code, we use a lot of MPI reduce, collective communication, which account for 75% of the time on the 8 cores. So the new code, after we change to 1 MPI reduce of an array of bigger message. Remember, if you do the old code, you pay a lot of latency cost. But here, you pay only 1 latency, but a larger array, okay? So then we compare the 2 codes. So we have 2 machines and 2 codes. You compare the 2 codes on one machine, 2 codes on another machine. So the new code is always better. It's significantly better. So for this one, it's so much reduced. When you increase the number of cores, 75% of the time is doing this communication, but here is much reduced. So sometimes when you start coding some algorithm very quickly, then you see performance is not very good. That you have to rethink many times. So where is do the profiling of the code to see where the code spends the time and how to improve. Sometimes the improvement could be very trivial. I mean, it's not trivial, but it's relatively simple. You just combine a lot of small messages into big message, then you reduce the latency cost. Okay, so I pretty much touched the major parallel ideas in the super-LU left-looking, right-looking distributed memory algorithm. And then there's a good different organization of the algorithm called multifrontal, which we talked about before. And there's a good code also. It's called a MUMPS, distributed memory multifrontal algorithm. So it's a right-looking kind of algorithm, but it's different from the supernodal super-LU. And then what they do is a symmetric pattern multifrontal factorization. They parallelism based on the elimination tree from both the tree and also when you get the big font. They do parallelism as well, doing the parallel, for example, GEMM. And then they use a dynamic scheduling of the dense operation. There's a symmetrical pre-ordering. So also for the non-symmetric matrix, this is for the symmetric pattern. So the non-zero structure needs to be symmetric. That means if you have start with a non-symmetric matrix, for the zero guy, you have to fill in 0. So it's actually padded some zeros. You do a little bit more operation. But it's easier to manage the algorithm in this way. So then they also use this weighted matching to get a big diagonal so that you don't need to pivot much on, during the numerical factorization, and expand the non-zero pattern so that you have symmetric pattern. The values could be still different, upper or lower, but the pattern has to be the same. Then suppose you have failed the pivots at any step, they will pass along the tree to the ancestors. So that's the general idea of this algorithm. So what I want to show you is, before we take the break, is I keep a little short survey of the available software codes people could look at. Because you see that for sparse direct methods, there are a lot of things involved. If you really want to get a good implementation, it actually takes a lot of time. So that's why people, when they implement the code, they put it up, make it available to the community. And people usually just download from the web to use. And in this little survey, you can see the different kind of factorization. Cholesky, symmetric indefinite LU, and QR, and also depending on different machines, there are different codes. And nowadays, you have heard about the accelerators, different kind of accelerator attached to the processor, to the CPU, such like GPU, FPGA. They become more active research, but so far there is not a very good, reliable code available. It's still at the research stage. So this survey you can get from my website, but I'll show you very quickly what it looks like if I can find it. Let me see where. Yeah, okay. not good. Okay. So in the beginning, it has a very high-level description about the algorithm, and then it's really this table. For sequential machine, you will get for sequential machine, you get so there's a sequential platform, so you get a lot of codes there, and it talks about what's the technique used, whether it's left-looking, right-looking, multifrontal, and what's the scope, whether it solves only SPD problem or non-symmetric, and whether some code has QR, and then the contact where you can get the code. And the shared memory machine, there are a number of codes available. Also, what kind of algorithm it's using. So by the time you get to the distributed memory machine, it's actually not so many codes available. And some of the code are more research code. You can download, but it's not well supported, well documented. And some of them very widely used is probably this MUMPS. It's a multifrontal code I just mentioned. And then PASTIC is a left-looking, right-looking. It's a combination of left and right-looking. Both of these are from France, two different groups. And SuperLU, that's we developed. It's mostly right-looking for distributed memory. So you can, when you need to do the large-scale calculation, you can go to here to get some code. And then also, when we develop sparse algorithms, we always want to test. And you cannot, in a dense case, like generate a lot of dense matrices of different feature. So Tim Davis, actually, he's a professor at the University of Florida, has graciously supported this effort to have a collection of a lot of matrices. If you have any matrices interesting problem, you should be submitting the matrix to him to put in this collection. I don't know, I haven't counted recently how many of those. It's a lot of matrices. So you can get of different characteristics from different applications, then you can test your algorithms. Okay, so let's take, so those are the references. And we'll take a break, coming back to look at the approximate factorization as a preconditioner. Exercise for this lecture is relatively easy. If you have time, you can do it. For the distributed memory code, we have already installed on the VirtualBox and also on this cluster. So you can go to this directory, home directory. There's a README, and also there's an example directory. Take a look at a README. So hopefully, by just looking at a README, you can run the example and take a look at the output, take a look at the driver to see how it works. And then for the one thing I want to do, the exercise is useful for you in the long term is to go to the website, download this multi-threaded version yourself, and try to install yourself. See whether you can compile the code, make it, and then go to the example directory, run the example. So then you go through all the process of how to install a software, some solver, say from the public domain. And as I mentioned, there are a lot of codes. So the different code has a different installation procedure. But that's a good exercise for you in the long term. Okay, so then we'll start talking about approximate factorization as a preconditioning. And I will talk about two different kinds of approximation schemes. So today is one scheme, and then tomorrow is another scheme. Let's see. Okay, so this lecture is about incomplete factorization. So this is actually, a lot of this is coming from a research paper that I did with Meiyue when he was visiting the lab for a few months. And then it turns out the result was pretty good. So we put this algorithm in the sequential code, SuperLU. So now if you download the latest version of SuperLU, it will have this incomplete factorization as a preconditioner. And then we use SuperNode, the version which is slightly more advanced than the previous version that Yusuf Saad has been advocating for many years. And also there's some different variants I'll show you. And then one of the big things we have done, we spent a lot of time, is to look at a large number of matrices. And all of these matrices, most of them, were downloaded from the University of Florida, the sparse matrix collection. So, and it's still not the entire collection. Okay, so preconditioning. So remember the direct solver, the major difficulty is the field, and you need to deal with it. It's very costly, even though once you get the exact factorization, you can solve the system very reliably. So then people start thinking about, in order to improve efficiency of the factorization, not to generate so many fields. So that means we leave out, drop some of the elements which are not significant from numerical point of view. And then we solve the linear system. Instead of solving original AX equals to B, we solve either use left preconditioning, this transformed linear system, or use right preconditioning, another transformed linear system. So two different ways of doing preconditioning. So the goal here is really to get a good preconditioner, this M, which is as close to A as possible. Then you will get the spectrum property, the eigenvalue distribution of this guy becomes much better. So if in a symmetric case, for example, its condition number is small, then the conjugate gradient will converge much faster. So that's the basic idea. And of course, if you can find that M is exactly as A, that's exactly like you do a exact factorization. But here we want something which is compromised in between. So we want this M is cheap to compute, cheap to construct, store, to invert, since we have this inversion kind of operator. And then also to parallelize. For nowadays, people use the iterative solver for very large scale problem. And all the preconditioners have to be parallelized. Otherwise, you jeopardize your original iterative solver. And then we want a good approximation. Okay, so those are the goals. But very often, these are contradictory to each other, and so you have to make a compromise trade-off. So in the sparse computation, it's a lot of trade-offs of different criteria. So the standard design strategy is we start with a complete factorization. So for example, you start with a SuperLU code, and then you say, I drop some elements to make it an approximate factorization. So we add approximation to make it cheaper to get to achieve this goal, and then hopefully not to compromise too much about the quality of approximation. So then I'll present two different, very different approximation schemes. The first is this incomplete factorization, usually called ILU, or in the case of Cholesky factorization, is IC, incomplete Cholesky factorization. The first category is structure-based dropping. It's based on the level of a field. So ILU 0, it's people commonly use this one, meaning that I just use the pattern of original matrix A. I don't allow any field. So when you do the numerical computation, if you have a field generated, you just remove that element. So in the end, your LU factor has the same pattern of A. That means you keep the level of a field. Level of a field, basically for each entry, you have how many these non-zero propagations, how many times it's propagated, updated to this entry is called the level. So the level of field, if it's 0, it's the same pattern as A. And the level of field is 1, meaning that you could generate one field, but this field is not allowed to propagate to generate another field. So the level of 1, level of K. So with a higher level of field, you get a denser and denser factorization. And if you set K to be infinity, then you get exact LU factorization. So that's the general idea. So if you decide you only want to allow the level of 3 or any level, then you can still have a symbolic factorization algorithm to go through the graph to see you have use a counter to record the level for each element, level of field for each element.
You just said that if you send k to the infinity, isn't k equal to the size of the matrix enough to get complete factorization?
Yeah, that's a good point. Yeah. I was just simple in my mind. That's a very good point. So you won't get a k more than n, right? So the level of field won't be more than n, right? So for the level scheme, for each element you can say record the level at which level it's already filled, and every time you update the graph, you update this level information. Then by the time this entry hits the k threshold, then you don't allow it to fill anymore. So the non-zero element. So that's the basic idea for this level. But then you can imagine this is entirely structure-based. Just to look at the graph, regardless of the numerical values. So from numerical point of view, it's actually not very reliable. Very often, it doesn't converge for iterative solver. So the more powerful scheme is the value-based dropping, which means you really, after each step factorization, it has to be done dynamic. After the update of each step, then you really drop the elements which are truly small, the numerical value, in some measure, which I'll show you. So this is more reliable. It's also difficult to implement because then it changes the pattern on the fly, right? So a good place to look at this ILU incomplete Cholesky is actually Yusuf Saad, the book. He has a book on iterative method for linear solver, and he has another book for the eigenvalue problem. So he used this ILU-TP, the most sophisticated one, which means this T is a threshold. So it's a numerical value-based. User gave a certain tolerance, and if the value is smaller than this tolerance will drop. And another one is pivoting. The code can do, this algorithm will do pivoting. So that's the most difficult one, the most sophisticated, but in practice, it's very reliable compared to many other schemes. So then in his ILU-TP, he actually proposed two dual dropping criteria. One is use this tolerance. And another one is sometimes this tolerance is not good enough to, say, preserve the sparsity. So he says that my secondary dropping criteria is I have another parameter called P, let's say 10, for example. Then I don't allow the number of field in each column or in each row to be more than 10. If it's more than that, I leave only the largest 10. So there are these two criteria to help reduce the field, the memory requirement. And in the sparse, in the super LU case, what we really want to do is not to lose the efficiency of supernode. So we try to redesign the algorithm. Taking this a step forward, a little bit a step forward, is to see how this column-wise or row-wise Yusuf Saad's algorithm could be improved by retaining the supernode. So it's just this is just a review of the supernodal left-looking algorithm. So here is your current panel. Everything here is done. Everything here is not touched. And the factorization algorithm is for each panel, we do the partial pivoting. We do partial pivoting here, okay? And then do the symbolic factorization to determine the non-zero pattern of the current panel. Then do the numerical factorization. It can be high-level blast operation. And then in the end, the triangular solution. And so that's the picture of one supernode update one panel. And in the memory, they stored sequentially as this. So you can patch some zeros here to do GMM, okay? So that's the idea. So the primary dropping rule, which we have adapted from column-wise code, is really try to look at each panel. This part is already factorized, right? So you have the L part here. And then in the old scheme, in the original Yusuf Saad scheme, one column here, you drop the elements which is smaller than certain threshold. Then imagine that if you apply that scheme column-wise to here, you can drop one element here, one element here, and one element here, there. So among the 10 columns here, your dropping could be randomly, could be anywhere among those rows. Then after dropping, this supernode is basically it's broken. So you don't get a supernode, you get a lot of holes there. And what we are trying to do is really to see that whether we can just look at the entire row of the supernode and design some metric. Say we drop the entire row. So if this ith row is removed, we still maintain the supernode, right? But then, of course, you need to look at the metric for this. What do you mean by this row is small? I can drop. So the questions or the algorithm is basically for the U part. U part is not supernode, so you just do scalar. It's the same as Yusuf Sad's scheme. So you look at each of the element. If it's smaller relatively to the column size of A, the current column, then you set this element to be 0. So the L part is a retained supernode. So for this supernode from S to T columns, if row size of this ith row, and we'll talk about what is the row size. If this row size is smaller than threshold, then we set the entire row to be 0. Okay, so then the thing here is actually we do the delayed dropping. So we actually drop the elements. We do the computation first before we drop. So the dropping is happened afterwards. And so this will save many operations. It may not save operations because you have to compute the entries. But in the end, it will save the memory. But then it will save operation for the iterative solver. So for the factorization itself, it may not save many operations. And then there are many choices of row size metrics. We'll take a look at that. So the row size, what do you mean by a row is small? You can use several criteria we have looked at. For example, the first criteria we look at is the average. So take the row vector, the sum of the row vector. This is the x is a row vector. You take the sum of the absolute value and take the average. M is the size of this supernode. And then if the average size is small, then we say we drop. So that's actually used by Anshu Gupta, his co-author in their incomplete Cholesky factorization. They use this criteria. Okay. Also in this Cholesky factorization, they maintain supernode. And then the second the metric we used is generalized mean. You take the this is the spectral norm, the 2 norm of the vector, and then divided by the square root of the size. So this is like a generalized mean. That's another one. And then the third one is infinity norm. So you just say, among this, look at the entire row. If the largest entry is small, then we drop. So then you can see that using this criteria, if the largest entry is smaller than the threshold, we drop, meaning that going back to the column-wise algorithm, every entry will be dropped also, because every entry along this row will be smaller than the threshold, since the largest is smaller. Okay, so this is very strong. And look at the 3 norms because of this relation. That's the smallest quantity. This is the middle one. That's the largest one. So then actually what you have done here is, since this one is the smallest quantity, using this metric, you can potentially drop more rows. So the first criteria is most aggressive. The third one is more conservative. So we tried all of those. And then we also modified the secondary dropping rule. In the old scheme, the original scheme, the secondary dropping rule just to say, look at the current column. If the number of non-zeros exceeding 10, controlled by the parameter p, right? Here we use gamma. If the current column is more than 10 size, we'll just drop retain all the top 10, drop all of those. And we find that it's very restrictive. So because throughout the factorization, the size of the values among different columns, they actually varies. It's not so much uniform. So if you use a strict, constant, this dropping, it's not very reliable. So what Anshu Gupta in their IC design, they actually do a little bit clever. So this P is adaptive for each column. So P of J is given by this gamma. For example, gamma is 10, or it's a certain value, the fraction, and multiply the number of non-zero of the current column. So this P could be, depending on the current size of the, the column, can be for some denser columns, you leave more. For some sparser columns, you leave less. Instead of just the P as a constant. So it's slightly improved. And what we have improved even further is to look at the entire area before the current column. So we look at this fraction at the current step J of the field ratio, the field ratio at J, number of non-zeros of total these, all of these columns divided by the number of non-zeros of the original. So it's a field ratio up to the current point. And if this field ratio is bigger, then we drop. We keep use this criteria to keep the largest. But you can have the situation that when you do the factorization, the previous field ratio is kept already very low. Then that means you have an advantage that you can, at current step, I can leave more. I don't need to drop a lot. If the field ratio is already big dynamically on the fly, then I have to drop more aggressively. So that's the general idea. So this is slightly improved. And then for ILU, this approximate factorization, it's even more difficult to do analysis. So it's entirely, a lot of this is based on the experiments. And in the beginning, I remember the first version of the paper, we did experiments on, say, 30 or 50 matrices. And the referee came back say, oh, that's too little. It's not conclusive, you just 30 matrices. So in the end, actually he worked very hard. I asked him to work hard. So we downloaded a lot of matrices from this collection, 232 non-symmetric matrices. We used the criteria that the dimension is not too small, and also not too big. Since this is sequential code, we cannot deal with a very big matrix. So we just say, go to the website. It's a very nice website, by the way. You can put in any, so for example, if you have SPD matrices, you put in the criteria, you can download all the SPD matrices. So here we put in the criteria, we want a 5K to 1 million, the size of the matrix, and we want unsymmetric. And also we want condition number is bounded. It's not too ill conditioned, so that we can, at least it's not artificially singular problem, okay? So with this criterion, we got 227 matrices. And also we got to add another 5 matrices. This is from our very beginning. We mentioned this fusion tokamak design, this ITER fusion, the device design. From that, it's solving the magneto-hydrodynamic equation. It involves a lot of coupled PDEs. So those are also very difficult problems. And adding together, we have 232 matrices, and we use apply right preconditioner, use restarted GMRES with the restart space 50. And initial guess is 0 vector, and stopping criteria is the initial residual reduced by a factor of 8 orders of magnitude, and no more than 500 iterations. So if it's more than 500, we stop. We'll claim that this failed. And then it's on one of the machines, which is earlier machine. So we'll take a look at the examples, the result of several modifications we have made. What's the improvement? So the first set of example is we compare with the column-wise. Remember, now we are doing the supernode, drop the entire row by certain criteria. And when we compare with the column-wise, it's very simple. We just set a maximum supernode size to be 1. So then the code becomes a column-wise code. And then we compare with, we look at, so this is supernode size, supernode version, C is a column-wise version, and then we look at the 2 different row size criteria, okay? So the factor construction is one criteria, then look at GMRES iteration, the total time, solution time. Then the field, for example, let's take a look at the first set of results. Here we use the row size is the this generalized mean. So when the the spectral norm divided by square root of m, if this guy, each row is smaller than the threshold, gets given by the tau is 10 to the minus 4, then we drop the entire row. So then you can see that the flops is actually, you do a little more flops for the supernode side version compared to the column version. The fill ratio also you keep a little more. So with this criteria, you always keep a little more compared with column-wise, so it's less aggressive. And then, but in the end, the factorization construction, so this factorization is just like a preconditioner construction to get to approximate LU, and the time is much better. So among those 200 matrices, only 138 succeeded. Then the average iteration count, it takes a little bit more iteration compared to the column-wise. But total time is reduced this is for all these succeeded matrices. So the second set is about a different criteria, so it's similar. And then we have 134 matrices succeeded. So that's how we compare. So basically, after this exercise, we found that supernode in the incomplete LU case, we get a less benefit using supernode compared to the complete LU, because here you drop a lot, so your supernode size is relatively small, so you don't have too much benefit. It's still better, but less than 2 times the speed up. So if you remember, when I look at the supernode complete factorization code versus the column code, we get more than 10-fold speed up, just the sequential, by using supernode. But for the incomplete case, we get only about 2x speed up. So what is not good against the supernode? First, the supernode size is small. You drop a lot. Secondly, the row dropping rule in the supernode case tends to leave more fillings. So that's get more operation, etc. And we have to set the supernode, the maximum supernode has to be small. For example, in the current code, the default is 20. But in the exact factorization, we set a maximum supernode could be much larger, like 100. So now we look at this more difficult problem. And the good news is that even for this multi-physics kind of simulation, this ILU is still quite reliable. And here I'm comparing ILU with the complete LU factorization. And the comparison, so this is a sequence of the same discretization problems, but with increasing size. So the size is from 17,000 up to more than 500,000. The number of non-zeros in the original matrix, and then so ILU time and the super LU time, the complete factorization time. So ILU time, it's the factorization time. You see it's much smaller than complete factorization. And by the time you get to the largest problem, complete factorization failed just because of running out of memory for this sequential code. So the fill ratio is reduced with this drop-in criteria compared with the fill ratio. So that's why, when problem gets big, the fill ratio gets big, the exact factorization you run out of memory. But ILU, you can still succeed. But of course, it's good to get a factorization. And the question is whether the GMRES, the preconditioned linear system, converges. And here you can see that iterations increases with increasing size, and then the time also increases. So it's you cannot maintain the same number of iterations when you're increasing the problem size. So it's still not like the ideal algorithm. You want to increasing size, you maintain the same number of iterations. Like for example, for multigrid applied for Laplacian or Poisson kind of equation, that have this very nice property. But for these kind of difficult equations, it's very hard to maintain that property. So then we compare a lot of different versions of different algorithms. So what I'm talking about here is that we compare a lot of solvers with different inputs. So you have a lot of combination of solver and inputs. The question is, and then I have a lot of matrices, several hundred matrices. So the question is, what's the best way to present the performance of this solver with such a large number of data? How do you say which solver is good, which is bad? And one of the things that I want to spend a little time to you is this performance profile, which was first proposed by George Murray and Elizabeth Dolan, when they were studying benchmarking the optimization software. So there are a lot of optimization algorithm software. They want to see what's the performance look like. Then they developed this pretty powerful tool to study the different solver input combination. So what does this do is, so we define, let's M to be the set of matrices. In our case, we have 232 matrices. And then S is the set of solvers. In our case, we have ILU, but we have different, we can set a different tolerance. So for each tolerance, you can think about it as one solver. For each secondary drop in the gamma function, then you can think about it as each solver. So for ILU, you can change the parameters to get a different configuration of the solver. So that's what I mean by a set of solvers. And then I define the fill ratio and the time ratio. So denote the fill ratio and total time needed to solve the matrix M by solver S. Okay, so for each matrix M, for each solver, what's the fill ratio, what's the time? So what does this performance profile is look at the cumulative distribution function for each solver, S. So there are two criteria. One is we can look at a fraction of the problems that this solver S could solve within the fill ratio X. So you look at each solver, you fix a solver S, and look at the number of problems, number of matrices, which can be solved with a fill ratio smaller than a cutoff for X. And also, when you look at the time, you can say the fraction of the problems that this solver S could solve within a factor of X of the best solution time among all the solvers. So that means you still compute this probability, the fraction of, but this time the criteria is time for this solver. So you divide it among all the matrices, but look at those matrices M, which has the running time of this solver relative to the best time of any solver. And if this time ratio is smaller than a factor of X. So based on this tool, you calculate these two quantities, then you can plot, vary your X cutoff. You can see all your solver performance. So let's focus on the left side here. The left side is the profile of the fill ratio, right? So it's the performance profile of the fill ratio, which means the fraction of the problems a solver could solve within a fill ratio of X. So the X could be 1, 2, 3, 4, 5. So basically, my solver, I changed I set up a different performance, set up different tolerance with 10 to the minus 4, minus 8, minus 10 to the minus 4, then area-based secondary dropping, 10 to the minus 8, and then the area-based adaptive tolerance. So it's a different, very different parameter setting that you get a different configuration of the solver. So that's what I mean by different solvers in this case. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 solvers, including the column-wise version. And then you plot. So for example, you say, look at this solver, this square one, the square black one, it's this one. This solver, look at the point at 5, meaning that this solver could solve 40% of the problems with the fill ratio, if the fill ratio cut off with smaller than 5 factor of fill. Does that make sense? So then you can ask the question, which solver is good for the upper curve or lower curve? So the vertical axis is the fraction of the problems a solver could solve with a fill ratio smaller than 5 or smaller than 8. So which solver is the best? Is the lowest curve the solver or the highest? Highest. So the highest curve will say that I can solve, for here I can solve for more fraction of the problems with the fill ratio smaller than 7, 8, like this. But unfortunately, the message I want to give you here is that for ILU precondition, also if you do this for any preconditioner without, say, any iterative solver without preconditioner, say GMRS, QMR, a lot of iterative solvers, you can do the same kind of with several hundred matrices, do this profile. And then you can see that they are actually not a clear cut. One is always better. So in this case, we have two competing configuration, this black square and this green triangle. So these two, in the beginning, this black one is better, but then later, this green one is better. And so it's complicated. And here is the time. Look at the time profile. And then the clear winner is this black configuration. So the black configuration is this one. So that's why, after this exercise, we set the code. The default right now, if you download, is using tau is 10 to the minus 4, and then adaptive secondary area. So that's a very useful tool in the future when you study this kind of different algorithm. They don't have a very good analytical reasoning for you to think about which one is good. So from experiment, then there are so many data, you don't know still which one is better. And by doing this performance profiling plot, then you can have a much better, visually has a much better idea. But of course, this is statistical kind of approach. It doesn't say, if you look at the individual matrix, it's still not clear. This is just say, fraction of the problems, this solver is doing better, okay? But it doesn't say which problem, this problem, some problem, maybe this one's better, but that one is better, okay?
Excuse me, just a question to the right figure. I thought that the sum in the particular column should be 1 because of the ratio.
No, so this is not the, so this is the ratio of the time versus the best time. So my definition of here is the ratio of solver S for this matrix versus among all the solvers. I take the ratio of time versus the best.
Oh.
Right, yeah. Okay, so then there are some other features which I think it's a little bit tedious so I will skip those, which you can read. It's pretty well described. And then there's something for this modified ILU. The basic idea is just since you dropped some elements at the off diagonal, you add those quantities put back in the diagonal as a compensation not to lose too much information. And that's something proposed more than 20 years ago. And in the Cholesky factorization, it's very effective. But it turns out in the non-symmetric LU, we did different variants of this. It's still not very conclusive. So this is, again, the performance profile of different versions of modified ILU. And then here in this picture, I put in the exact factorization. So you see the exact factorization, it's not very good. So if you can succeed with the ILU preconditioning, it's always good. Okay, so we'll skip this then. So the last thing, I think we have about 10 minutes, I want to show you is to compare the ILU. So we did one version of ILU, and people have been doing some other ways, different method. So we want to see what's the performance advantage of each of those. The first one we'll compare with is Yusuf said, the first version of column-wise the ILU. And then he has this code. In fact, it's available from his website. It's a Sparse kit. It includes, in addition to ILU, and also a number of iterative solvers. Essentially, it's most of the algorithm in his book were implemented in this code, Sparse kit. So if you Google search, you'll find it. And the algorithm is a row-wise algorithm. There's no supernode. Then the secondary dropping uses fixed constant p for each row. And there's this multi-level ILU scheme is very powerful also. It's called ILU pack. He was actually a postdoc of Yusuf when he was doing this, developed most of this. And later he has improved a little, but most of the idea, two of them, they developed together. So this one is very different from our the algorithm I just mentioned. This one is used inverse-based approach. At each step, it monitors the norm of the kth row of the inverse of this L factor. And because you don't want the inverse to be big, then your algorithm becomes, the approximate LU becomes unstable. Then if the inverse of this current row is big, they will say it's too large. Then we don't do the pivoting now. So we delay this pivoting, move to the next level. Then starting from the next level, so for example, at the second column, you encounter this situation. Then we'll say, we stop, the current level is down. Then we go to the next level. Next level, you have maybe n-2 altogether, right? And I'll treat this n-2 as a complete new linear system, the new matrix. I'll do the scaling, equilibration, everything from start. So that's how they, with this scheme, they set up this multi-level scheme. They restart the delayed pivots in a new level, okay? And then there's something very different also, another very different approach is called the sparse approximate inverse. So here, I'm not trying to find a M, which is approximate A, but I'm trying to directly find the M, which is approximate to the A inverse. Then you can imagine it's probably hard, right? But then they have to do some restriction in order to get this to work. So for example, they have to make the pattern of the powers of, so first of all, they have to sparsify A. And in order to get this, because if you look at a sparse matrix A, do the inversion, then you get a dense matrix. That's generally true. For any inverse of a sparse matrix, it's going to be dense. So what they do is they first to use a threshold to sparsify the matrix A to get a sparser pattern, and then look at the pattern of powers. Because A inverse, you do the Taylor expansion, is just the power of 1, 2, 3 adding together. They say we just want to look at the power of 5, which is essentially like you are restricting to level of field to be 5, for example. So to first sparsify A, and then to set the n levels to keep the level of neighbors, not to go to too many levels. Otherwise, you get a very dense matrix, and that's a parameter. So we did the experiment with their default. This code is available with a default setting using threshold to be 0.1 to drop the elements which is smaller than this, and n levels to be 1, which is relatively conservative, but it's their default. So then we found that only 39 matrices converge. So it's very, not very reliable, not very good. And not only that, its failure rate is high, but also it takes a long time for those matrices, even for those converge. It takes 62 hours to construct the matrix, this approximate inverse. And then after that, 63 hours to do the GMRes. So in the end, we say we're not going to compare with that. So now we compare with the three, these available codes, our supernodal ILU, and then the ILU pack, and the sparse kit. Again, we use this performance profile. And we set the parameter. We chose the parameters. Each code has a different set of parameters. They have different meaning, but we try to set them as close as possible, almost the same, from the point of view for comparison. So then you can see that this supernodal, our new supernodal version, is always competitive with ILU pack and slightly better. For the time, from time-wise, it's better. And ILU pack, both of these is better than a column-wise sparse kit from sparse kit, both from field ratio and time-wise. Okay, so it's very good. And then we look at, as said, for ILU or iterative solver, it's very hard to say which one is better. Even if from, say, performance profile, we see that this ILU pack and our supernodal supernodal version, it seems like similar. But then when you zoom in closely, look at the problems closer, then you will see that they are comparable, right? So supernodal version, our version is slightly faster. ILU pack has slightly lower field. But none of the preconditioner works for all problems. So that's the situation. unlike direct methods, it's always work. None of them work for all the problems. And furthermore, the two methods, they don't solve the same set of problems. So for example, they fail roughly the similar portion of the matrices, but they don't fail the same number of matrices. The same kind of matrices. So SuperLU succeeds with 142. IOPAC succeeds with 130. It's similar. But both succeed with 100. So there's an intersection of problems that they can both solve, but then there are the different subset of problems. One can solve, the other cannot solve. So that's why in reality there are so many different solvers on the market. They are kind of serving as a complementary to each other. You cannot say, oh, I will just use this method, it will always work. And if you're lucky enough, you work in one application area, maybe one solver is good enough. But sometimes even in one application area, when you change the PDE parameters, then the different solver will behave differently. So that's the unfortunate situation. Unlike in a dense case, you can probably just use, scalar pack, or there's another set of effort called elemental. This maybe two sets of packages, then you can pretty much solve all the problems. But in the sparse case, it's much more complicated. Okay, so just to summarize this lecture. So what we have done in the research, we get a secondary dropping. It's more reliable, use area-based, so it has more global information. And then we use adaptive P, also adaptive tolerance. And then we have a lot of imperative study of this modified ILU. So the summary of the experiment, so we succeeded with only no more than 70% of the success rate with several 200 matrices. When it works, it's much better than direct solver. So when it works. And supernode is useful, but to less extent compared with complete LU. Secondary dropping, then there's the software. And then the difficult question is still there's no good solution is how do you get a scalable parallel ILUTP? Remember I showed the compared to the other approximation factorization like the paracel, this approximate inverse. The ILUTP numerically is actually very robust, very reliable for all very difficult problems, even for the fusion, the multiphysics simulation. But then you have all this sequential dependency, and then you have for arithmetic intensity is essentially very low. It's much lower than exact LU. So it's very difficult to do this in parallel. And I think we can put the same algorithm in the shared memory code, the SuperLU-MT, very easily. But right now we don't have a good solution to distribute it in SuperLU, for example, or in the multi-frontal code. So in both this, there's no ILU in complete preconditioner in the parallel. So then the reference, what I talked about, all these experiments are the modification. The supernodal version is in this paper. It's everything, all the detail, a lot of references there. And of course, Yusuf said the book is a very good resources for all this. And then the good paper, there are a lot of references, but I'd like to just mention this paper. This is a very good survey paper. It contains almost 300 references, including some references. Some people have tried to do parallel ILU, and without too much success. But it's in those reference lists. So it's a very good comprehensive paper. So then the study. Okay, so there's not too much. We have the code installed already in the directory in your hands-on exercise. So you can run the example ILU preconditioner plus GMRES to maybe get some matrices from Florida, and then to see how it converges. And then there's also a little bit more involved. This is the experimental hands-on exercise incomplete Cholesky, which was developed in a course by Patrick Amistoy from France. So they have implemented a complete version of this complete Cholesky, and then they set up all the skeleton, the framework to do incomplete factorization. So if you have time, you're interested, you can just implement this routine in the file, in this file. It needs to add some lines of code to make it a complete code to do incomplete Cholesky. Cholesky is relatively easy. There's no issue about pivoting. So that's why this is a good exercise. So that's this lecture is a good time to stop. And then the next, tomorrow we'll look at another way of doing approximation, which is much more parallel. And in fact, we have the code available already in large-scale parallel computation. But ILU is relatively difficult, more difficult.